Hello everyone, this is Mr. 13 Things, and we're in the middle of a discussion of how we can take students beginning in, I would argue, fourth grade, and have them learn to translate, rotate, and mirror or reflect shapes using vector mathematics so that they can keep up with what they're doing in an Xbox. So they can maybe quicker and earlier learn to apply some of that same work to either 3D visualization or work inside the body or inside the nuclear power plant or inside the solar cells. Get them to the point where some of their mathematics catches up a lot earlier to what Steve Jobs and Bill Gates and all those other great innovators have either done to ruin them or to make them more competitive in the new world. So what I'm going to do here is I'm just going to keep going on my little dual thread here. I'm going to kind of maybe fill you in a little bit on what I think Sal Khan's doing off the screen when he does this stuff. So I'm going to more or less go ahead and I'm going to just kind of use my little pen tool here, and I'm going to kind of fill in some areas here. I like the red, and I'm going to go ahead now. I'm using the pen tool, suck that up. I'm going to take that, and I'm going to go ahead and I'm going to make an area there that's red. And we're going to see why I'm going to go ahead and erase that, and we'll talk about what we're going to do here in terms of standard colors. Edit, cut. I could have done, I'm going to go back to the green. Remember, X is red typically. X is red in most 3D drafting. Don't know why. We'll look for the history of that. X is red. So I'm going to make a little red circle here. It's not that red. It's a different red, but we'll live with that. Y is green. All right, so I'm going to pick up the green here. I'm going to go ahead and make a green dot here. And Z is blue. Don't know why that is. Those are standard colors now in the visual framework. Kids are used to those. Have them check. Don't tell them. Let them go home and look it up in their Xbox. All right, so you got these three colors. Now I can go ahead and I'm going to take this all apart. I'm going to edit, cut, all right, edit that out. I'm going to go ahead and edit, and we'll start with a clean screen here a little bit, and we'll go through some of the basics for some of you that want to, there's better places to learn how to multiply a matrix by a vector, but I want to point one small nuance out here. That's what we're doing here. I want you to think about teaching students and doing it yourself this way so you can get the concept of what a transformation is and how one thing is acting on another. The mathematics turns out to be exactly the same. But what we had here, we're going to go ahead and now I'll just use the blackish one here. If we have this matrix right here, and I'm not going to colorize this. If I have this matrix here and it is, we talked about it, -1 and -1 and 0, and I go ahead and I'll put a 1 down here. If you remember, this is the X, that's the Y, and that's the Z. You can do it that way, but now think about, it's not a hassle to actually do this, is it? Select that. Now it's the pen. So now I can go ahead and see, I'm going to go ahead and select that. That's my pen. Go here and I can kind of go, that's my red, that's my X. Now I can go here, since I did this kind of palette-y over thing here, that makes it a little bit easier, doesn't it? Go back and forth up here, -1. Why I never figured that out, why AutoCAD did not have that in their basic tools, I will never know. It's actually there, but some of us were trained badly. So we're going to go back and forth to clear our palette, and then we're going to make that 0 and the Z, and realistically I'm going to go ahead and try to get a black color up here so I can deal with the black as well. Apologize for that, which lets me to suck up that, pen back and forth, and then I've got 1 there. So this describes a point. So this is a point in space. Now, prior to this, of course, you may want to talk about relative coordinate systems, in your Xbox, but we'll just leave it at it's a relative point in space. And now we're going to go back one more time to the transformation matrix, right? And we're not necessarily going to colorize this because students eventually are going to want to learn to think about this as a whole thing. This is a point and this is a transformation, right? Transformation or a transformation matrix. Now, I will point out here as an aside, as I've had great conversations with my kids' teachers, and based on some of my experiences dealing in engineering and then dealing in an engineering classroom, I remember coming in one day to one of the better teachers I know and saying, students don't understand anything about place value. My concept of place value was 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. When I was talking about place value, I was talking about where something fit into this number, this matrix number. What the 6th grade teacher was talking about is students didn't understand the concept of 537.64. The 4 is in the hundredths place. The 6 is in the tenths place. The 7 is in the ones place. The 3 is in the tens place. The 5 is in the hundreds place. I don't know which is more important to really understand. Eventually, that kind of numbers are going to come at you in a lot different ways than just like that. So, but I would call them equal. You know, the concept that numbers are going to fit into a visual construct and they're going to behave differently in different situations is something students can grasp. Especially if, in fact, you always deal with your matrices in 4 by 4 and all of your points are in a stack of 3 and then one more. Sure, you can dual account. You know, you can continue, and I would expect that you'll need to until either some of these organizations figure out what we are, in fact, training our kids to do. I'm going to grab that one more time. All right, so I don't think it's too long. You're always going to want to go back every now and then to the -1 and then go ahead and, let's see, I'm going to suck this up. You always want to do some dual accounting, you know, on students, with students. Grab that again, grab this back and forth, and then -1. So getting students to realize that these are the same thing. And, you know, maybe you want to even show them that it looks like that sometimes. That's real. But now once you have this concept of this is a transformation and this one is the identity, right? That if you multiply or transform anything by effectively 1, you'll get the same thing. And now this time I'm going to go ahead and work this out. It's going to take a lot of work, but it's going to be 1 times -1 plus 0 times -1 plus 0 times 0 plus 0 times 1, right? And then the next one is going to be 0 times -1, right? Plus 1 times -1. And if you notice here, my choice of -1 is not a good choice. I know that. I regret it, but we'll live with it for now. Plus 0 times 0, right? Plus 0 times 1 is my second point. My third point is going to be 0 times -1, right? Plus 0 times -1 plus 1 times 0, right? Plus 0 times 1. And then the last one would, of course, be 0 times -1 plus 0 times -1 plus 0 times 0 plus 1 times 1. Now, apologize for the chicken scratch, but all of a sudden, perhaps you can start then colorizing what these numbers are. So these -1s here, in effect, right, are all this same -1 there. So if you go to here and you colorize, and these are things that, you know, you can do on a board, but you can do it in computers just as well. So I'm going to go ahead, and that's minus, I have to learn how to use the computer is the problem, right? There you go, -1, back and forth. Highlighters, so that's -1, and this is -1, and this is -1, and this is -1. That's that -1, whereas opposed to, again, pick up the green, back and forth. This is that -1, that's that -1, -1, -1, and this 0, we'll finish up with that. You're going to go ahead and suck that blue up and go back and forth here. And then this is that 0 here, right? 0, 0, 0, 0. And then this last one would be, of course, the black. We're going to go ahead and suck up that information. A big part of this, I will let you know, is in the end, I want to point out that students shouldn't, will not, and would be not emulating what everyone else does if they did this many more times than once or twice. Learning that this is a matrix and you multiply a matrix by a vector and get an answer in a calculator. Really well done by a TI-83. One of the best places to do it is on a TI-83 calculator. And if you think there's a cost to that, go out and check out the TI-83 website, which has an emulator that will put a fully functioning TI-83 emulator on any Windows desktop. No kidding. So any student who has access to a computer at home could have access to that. There's other great places to do it, matrix calculators, but we'll talk about that in another way, shape, or form. So what you want to summarize there, and there's a whole lot of time here, we'll try to edit this down, but learning to have students, I'm going to put this up, notate their points in a column vector format with X, Y, and Z. The key thing being that, and then a 1 kind of scale factor. And then learning to deal with transformation matrix, which we will see, alluding to the next video, is a combination of a rotation scale matrix here, and then a translation vector here. Learning to do that, they will then be able to quickly master and animate using any variety of things, including crowdsourced methods within class, as certain people can grab the first row's calculations, the second rows, the third rows, the fourth row. If you have 8 rows in your classroom, you now then can have calculation redundancy, whereas row 1 and 5 can do this calculation, and row 2 and 6 can do this calculation, and row 3 and 7 can do this calculation, and row 4 and 8 can do this calculation. What are we looking at? 32 students perhaps in your classrooms. You now have some calculation redundancy, and you can start to make your classroom look a little bit like a computer. No kidding. Thanks for listening.